So last time we talked about how to build block encodings, and in particular, how LCU can be used in order to be able to implement particular block encoding. Now we're going to be transforming into the second part of it. It's actually kind of funny I use the word transforming because the algorithms that we're going to be looking at actually allow us to go one step further beyond the block encoding and ask, well, what can we do with these block encoded matrices? So in particular, what I'm saying here is before we said, okay, let's assume that A is is a matrix. Then we provided a generic methods for block encoding it, meaning that we find a way of embedding A inside a larger matrix of this form. What we'd really like to do now, if we've got a block encoding like this, it's cool that we've got the ability to be able to represent A, but we'd like to be able to do stuff to it. So what I'd like to be able to do is do something like, well, if I've got U and V equals a B over beta, say, and other stuff out here, can I implement a block encoding of A over alpha plus B over beta? I guess maybe I should put primes here because the normalization constants could be different. Can we do the sums of them? And the answer to this is sure, of course we can. What we can do is we can just add an additional qubit up here and then use LCU in order to be able to sum U and V together in order to build the sum of the two. So this shows that block encodings can be um, added. We can actually also do similar things to be able to multiply. In effect, what we can do is imagine what we had is I wanted to build a matrix that is of the form A plus B A squared. What I could do here is I could say, well, I'm going to build a register that ends up keeping track of the different powers of A that I want to do. This would be the first power, and then this over here would be the second power. Then what I would do is I would say, okay, I'm going to build an additional register over here for storing the coefficients of that, feed that into a prepare circuit, feed that into a prepare circuit where I define prepare and select last time for LCU. Then what I do is I would do the following. I'd build a select circuit that takes in the first one, and then a select circuit that takes in the second one, then controlled off of these two qubits, and then prep dagger and prep dagger. Now this over here will allow me to code up whether or not I'd like to do an A squared or an A. So for example, if I wanted to do an A, then I would just put a 1 and a 0 in this. If I want to do A squared, then I'll need to apply the select circuit twice for it, and I can put two ones up at the top here. So this gives us a way of doing A or A squared, but if I change this up and I now put in a box that I'll call prep 0 and prep 0 dagger, what I can do is I can use the LCU lemma in order to be able to go forward and actually build an arbitrary combination of this form over here. And by expanding this out, I can end up actually implementing a larger block encoding of a matrix that's f of a question mark, question mark, question mark, or any analytic, meaning something that has a convergent Taylor series. F. So basically what you do is you just sum the Taylor series up to some appropriate order, approximate F that way, and then I can implement using a polynomial approximation any function I feel like. And this was the initial idea behind a whole bunch of quantum simulation algorithms that ended up coming up, such as the truncated Taylor series method, which I'm not going to cover here, but you can see that in my previous recordings, as well as the improved quantum linear systems algorithm, which is the descendant of HHL that provides exponentially improved scaling over the OG version using this type of a circuit. So this gave us nice ways of doing this on a quantum computer. But there's one annoying bit that ends up coming out of it. Biggest annoying bit that we end up seeing is the sheer number of qubits that we end up needing in order to be able to do the appropriate polynomial transformation this way. Especially if I use a unary encoding, if I wanted to go to degree D, then I'm going to need order D qubits in order to be able to do this. I can do a little bit better by going to a binary encoding at the price of course, more sophisticated control logic here. But the point is that it's kind of a little bit messy. So question is, does there exist a smarter way of implementing our goal of computing a function, a block encoding of a function of the block? Now, the first step towards this actually began in the 1970s. It turns out that actually there's a technology that has existed since then called liquid state NMR quantum computing. Anytime you've gotten an MRI or you've done an NMR scan of some chemical or something else, that is actually using this technology, which takes which uses quantum spin resonance in order to be able to deduce things about matter. But the thing is that essentially people were manipulating already quantum systems using or primitive technology, and in particular, they would want to do things like an RZ gate on some of the nuclear spins in these systems. So if you've got this, then there was a problem because in practice, what you would have is you'd have some big solenoid making B field go down across your sample. And there might be problems with the B field, or there might be problems with the amount of time that your sample ends up staying inside this field. And so because the sample might be, in the field for a little bit less than you'd want, you might end up getting a gate that might be RZ minus some phase difference phi. And this means if you got some fluctuation on it, you can get some problems in your gates. So then the question is it possible that we could actually build a sequence of pulses that we would end up putting through here to make it robust, i.e., to end up making a transformation that would end up taking RZ theta in and then mapping it to through a following type of transformation, maybe something like this, where we have for input angles near the top that the function of the output versus the input is essentially static up here. It really doesn't change much. And this would mean that it's essentially insensitive to the value of phi that we end up putting in, because if I put in a value of, say, phi there, then this value here and that value, which is the original one that we might want to hit, they're going to be basically the same. So the question is, can we implement a polynomial transformation? And such a polynomial transformation that would approximate this might be something that would look like this, where we've got maybe some small jitter, because obviously we can't have a function that's completely flat and precisely represent that with a polynomial unless it's the constant function. So means that we're going to need to have some machinery for doing this. And in the 70s, the NMR community basically ended up finding a pulse sequence called the BB190 pulse sequence that ended up taking the following form. let's imagine we've got u of phi 0 through phi d over here is defined to be equal to e to the negative I. Um, Actually, let's make it plus phi 0 z times the product from j equals 1 to d of, let's call it ry of an angle theta over here, followed through by an e to the I phi j z. So the idea basically here is that we're doing a sequence of non-commuting rotations in the following way. We've got like a z rotation that we're carrying out in the block sphere, followed up by rotations about the y-axis, which I think is this one, but I'm not positive. All right. So in any case, by repeating these over and over again, our hope is to be able to implement a non-linear transformation on the input rotation angle phi to be able to build a function that ends up looking like this. Now, it seems strange, right? Because you'd imagine that you've got all of these different operators coming in. It seems, and they're all linear operators. It seems strange that we'd be able to find a nonlinear response in the angles that end up coming out of it. But in fact, it's possible. And this pulse sequence actually worked incredibly well. And it required, in particular, some specific choices, phi 0 to phi j, that I won't bother you with lately. But the idea is, at a high level, we can actually just rewrite this. And if we want to rewrite this, what I can do is I can say, okay, well, if I define ry of 2 arc cos of x, i.e., if I let my theta equal to cos inverse of x here, then this y rotation ends up actually taking a look like a familiar object. It ends up taking the form negative 1 minus x squared, square root 1 minus x squared, x. What does this look like? Well, this looks like a block encoding. This is a block encoding of x, okay? So that's a scalar block encoding, and we'll go beyond this later. But essentially, what this BB190 pulse sequence that people designed in the 70s was able to do is it was able to map this forward to p of x minus square root 1 minus x squared q of x square root 1 minus x squared q star of x p star of x for polynomials p and q. Now, they didn't specify it like this. There were individual pulses that people, of course, ended up coming up with for different purposes. But as viewed now through the lens of quantum computing, this control technique that was originally just used to stabilize rotations actually gives us a way of manipulating a block encoding. So that's what we're going to do. We're going to view this first as a primitive example of a manipulation of a scalar block encoding inside a unitary matrix. Then what we're going to do with that is we're going to talk about how to generalize this idea in order to be able to apply it to generic matrices that we're encoding in here and use these tools in order to be able to manipulate those. And that idea is known as a quantum singular value transformation. But this case in particular that we're talking about here is often known as quantum signal processing. So let's talk about how to actually build this. And the question is what P's are possible. So the claim, um, the transformation of x square root 1 minus x squared negative square root 1 minus x squared x to well, I'll save this. This guy up here is possible using the above sequence that I had here, this thing. Let's actually just, you know what? We use technology to get, okay, using that guy, and using this, if and only if and only if the following statements hold. One, the let's zoom out a little bit so you can see the transformation. One, that the degree of P is less than or equal to D, and the degree of Q is less than or equal to D minus 1. And here we're using convention that the degree of the zero matrix is always equal to minus 1. 2, P is even and Q is not even, or P is odd and Q is even. So basically, the polynomials that we can achieve for this, we can't do everything. We can only do polynomials that have definite parity. So for example, I could do a polynomial P that is an even function, like P of x equals x squared. But I can't do, for example, P of x equals e to the minus x, which would just be something like this. Because you can see e to the minus x is neither even nor odd. But in general, any polynomial could always be written as a sum of even and odd. So LCU can be used to express this as P even plus P odd. And so we can use previous tricks that we discussed in order to be able to do this in general. Also, I should note there's other techniques such as generalized quantum signal processing that allow you to do directly even and odd functions, but I won't be talking about that here. I'll just be talking about vanilla quantum signal processing for the moment. Okay, so that's the restriction. And the third one, which is the most obvious restriction of them all, is that the absolute value of the p polynomial squared plus 1 minus x squared times the absolute value of the q polynomial squared has to equal to 1. Why is that? Well, the reason why this has to be true is because of the fact that this needs to be built inside a unitary matrix. So because it needs to be built inside a unitary matrix, the rows and the columns have to all be unit vectors. And thus, whatever polynomial p and q we build, it has to correspond to a unit length vector. Also, this ends up creating some restrictions on this. So, for example, another restriction that's imposed by this is that p of x has to have domain and range in -1, 1. Otherwise, there's no way that I could end up finding a q that would end up matching this. So this ends up restricting our range of different polynomials. And now, just as a little bit of an aside, there are polynomials that you can end up seeing quite easily that end up satisfying these conditions. For example, Chebyshev polynomials, Tn of x and un minus 1 of x, um, trivially satisfy these. And the reason why is that TNs and UNs, they're all functions of definite parity, and they satisfy two. The next thing to note is that they can be constructed by the matrix U of 0, 0, going down to D over here. And this will end up yielding, in general, the matrix TD of X, negative square root 1 minus x squared ud minus 1 of x. Square root 1 minus x squared ud minus 1x and td of x over here. So just by plugging zeros in, we can end up building block encodings of Chebyshev polynomials. So we can see that there's at least some large families of important polynomials that we can build. And Chebyshev polynomials, I should mention, like if you're going to spend some time learning about a family of polynomials, Chebyshev polynomials are probably the right thing because they are just the best polynomial. Like look them up on Wikipedia and you will certainly agree with me that Chebyshev polynomials are the best polynomials. Okay. Keith, but so this says that there exists some solution over here. But the claim that I was making here for quantum signal processing is more broad. It says not just Chebyshev polynomials, but any polynomial that ends up satisfying this has a set of phases that correspond to it, and every set of phases will also correspond to a particular polynomial. So to prove it, what we're going to need to do is we are going to prove it by induction. And there's two directions because it's an if and only if statement that we need to demonstrate. The first direction we need to say is for all d greater than or equal to 0, the function phi u of phi 0 through through phi d will generate a set of polynomials that will satisfy all three properties. Now, the way we end up proving this in general is the exact same way we always go through any inductive proof. We start out with a totally trivial base case that is easy to demonstrate, and then show how we can use that in order to be able to generalize to the next slightly non-trivial case. Now, the base case that we would like to demonstrate for the forward direction of the proof is the d equals 0 case. So what ends up happening with the d equals 0 case? Well, in this case, our u phi of x, or u phi is actually just simply going to be e to the I phi 0 times z, which as a matrix, we can see is of the form e to the I phi 0, e to the minus I phi 0. Wonderful. Okay, so if we're viewing this as p up here, then we can see immediately that the degree of p equals 0 because it's independent of x. There's no x coming in here at all. And I should say degree p of x. And that is equal to d. So this works for it. Now, the degree of q that we end up getting here is equal to -1 because this polynomial over here is 0, and we chose the convention that the degree of 0 is -1. So based on that convention, then this is equal to d minus 1, which is satisfies condition 1. So condition 1 works. Now, condition 2, we have that p of x is even because it's a constant function. And q is 0 implies that it's not even. So therefore, we end up having a set that has definite parity that ends up coming out the other side. So this is good. 3, the because it's in a unitary, this is trivial, but we can end up seeing that the condition also ends up applying because the magnitude of p squared plus 1 minus x squared q squared. In this case, q is 0, p is e to the I phi. So this is e to the I phi 0 squared, which is equal to 1. And thus, case 3 is satisfied. And this is true for all phi naught. So thus, therefore, there exists a D such that the forward direction works. Now, what we're going to need to do is we're going to assume that for that phi of u of phi 0 through phi d minus 1 will end up working. Satisfies the 3 conditions. Then at that stage, what this implies that u of phi 0 through to phi d minus 1 can be written as a polynomial of the form p negative q square root 1 minus x squared, q conjugate square root 1 minus x squared, p conjugate. Okay. And thus, we end up having that u0, u of phi 0 through phi d will end up satisfying the following. This will end up giving us p negative q square root 1 minus x squared. I'm just plugging everything in to the series expansion, or not the series expansion, the product definition of this here. So I'm just adding essentially one extra query to this guy over here, which we'll call OX. Star O of X times e to the negative I phi d z plus, sorry. Now, if this is true, then this is just going to be equal to the above expression, which is p negative q square root 1 minus x squared q conjugate square root 1 minus x squared p conjugate times x negative square root 1 minus x squared root 1 minus x squared x times e to the I phi d 0, 0, e to the minus I phi d. Okay, now this is just an elementary matrix multiplication that we can do. Doing that matrix multiplication gives us e to the I phi d times x p of x minus 1 minus x squared q times e to the negative I phi d negative square root 1 minus x squared times p plus x q. Then multiplied by its conjugate, e to the I phi d negative 1 minus x squared p conjugate plus x q conjugate. And then finally, e to the negative I phi d times x p conjugate minus 1 minus x squared q conjugate. Okay, this guy is our target. Now, let's go through and take a look at some assumptions. Um, one, if p of x is even, and then this element up here, which I'll call p tilde, then p tilde will be a xp minus q plus x squared q. If we take a look at this, well, this is going to be then a odd function. The q over here has to have the opposite parity in order by our inductive hypothesis. So q, if p is even, then q has to be odd. And thus, this has to be odd as well. So therefore, p tilde, which is the polynomial that we end up finding over here, is odd. Now, if p of x is odd, we can go through the exact same thing. We end up getting that xp is now going to be even. Q will have to also be even in this case. And similarly, because x squared doesn't change the parity, we have x squared times q. That also has to be even. This implies that p tilde is even. And similarly, going through, what we end up finding is that p of x, that q tilde of x, which is the corresponding polynomial that we end up seeing here, has to then be even if p tilde is odd. And similarly, is odd if p tilde even. Okay, so this shows property 2. Similarly, if we take a look at the degree of the polynomial, we end up seeing that the degree of p is by assumption less than or equal to d minus 1. And therefore, because of the series that we ended up getting, p tilde, the degree of p tilde over here, has to be then less than or equal to the degree of the first term, which is less than or equal to d, the maximum of d, and d minus 2 plus 2, which is equal to d. So therefore, the degree that we end up getting for p tilde is less than or equal to d, given that the degree of d is less than p is less than or equal to d minus 1. Similarly, we end up finding that the degree of q tilde is less than or equal to d minus 1. Great. So that satisfies the second of the properties. The third one, which is unitarity, holds because it's manifestly unitary. As I said before, it has to hold because the function is built already inside a unitary matrix. So we don't even need to worry to check that about checking that. So this shows that therefore, if the case of d minus 1 will yield a p and q that satisfy criteria, then d will also implies by induction from the base case d equals 0 that all d greater than or equal to 0 will. Wonderful. So this shows the forward direction. This shows that if we use the quantum signal processing protocol, then we will always generate a polynomial transformation that ends up taking the particular form. But that isn't quite giving us what we want. We want an if and only if statement. And further, we would like to be able to do something like this over here. We'd like to be able to build a particular polynomial that will transform a block encoding to anything we'd like. So how can we go through and do that? Well, we need to show now the backwards direction for this. In the backwards direction, we're going to show through an inductive proof. Okay, so what we're going to need to do is we're going to need to show that all polynomials of a particular form can be built using a QSP sequence of the commensurate length. And QSP is just an abbreviation for quantum signal processing. So the basic idea behind this is what we need to do is we need to begin by starting from the harder path, which is the reverse path. So to give you an idea about the reverse proof, what I want to remind you about how we go forward and end up synthesizing an arbitrary unitary for a circuit. So the way that we ended up doing that, and you can see my previous lectures, or you can look at Nielsen and Schwang or some other reference for this. But the key idea is, if I want to be able to figure out a sequence of gates to implement U, one way of doing this is to say, okay, I'd like to be able to find a product from j equals 1 to, I don't know, n of some fundamental gates G over here. This is equivalent to saying that what I'd like to do is I'd like to be able to find some sequence of G's such that U times the product from J equals N down to 1 of GJ inverse is equal to identity. So all I've done is I've just taken the inverse of both sides and used the fact that AB inverse equals B inverse A inverse. Okay, so that's the strategy that we're going to do here. What we're going to do is we're going to try to peel back this one layer at a time. And we're going to want to show that we can, if we've got a larger degree polynomial that we want to deal with, we can always reduce it to a lower degree polynomial. And then from if we can end up showing that that lower degree polynomial is always achievable, then we can end up using an inductive argument to be able to prove the reverse direction and say that, yeah, we can always end up finding a set of phi's to build any polynomial just by taking a polynomial of degree 1 higher and reducing it to a lower degree polynomial that we can prove that we can synthesize. So how are we going to go through and do this? Well, we need to start again with an inductive argument with, again, a base case. Base case is going to be, you guessed it, degree 0. So if d equals 0 here, what I want to do is I want to be able to show that all p of x satisfying the above assumptions can be built. Okay, great. So how are we going to do that? Well, we're going to do it for the case of the degree. Let's assume that if the degree of p of x equals 0, then p of x has to be equal to e to the I phi up here. And similarly, this one is its complex conjugate, e to the minus I phi over here. And then if this is true, if it's also a valid one, then the degree of q has to equal -1. So these have to be 0 in here. This is just equal to e to the negative I z phi. And this corresponds to the case where phi 0 equals phi. So trivially, we can actually end up building every polynomial that satisfies that criteria. So that ends up working just fine if that's true. Now there's an additional case that is a little bit more annoying. So what this did is this showed, okay, if we have a sequence of length 0, then we can end up synthesizing it. But what we need to be able to show is we need to be able to show that we can do it for any value of d. So we need to be able to do this in the following way. We need to be able to say, well, what if the degree of p that we want to build is equal to 0, but d is greater than 0? Can we always end up achieving this as well? Well, we can end up doing this using a following observation. What we can do is we can say, well, let's build this to be e to the I phi 0, 0, e to the minus I phi, which is our target that we want to build. And now the remaining junk that we have from the d operations is going to be of this form. It'll be e to the negative I phi j plus I, sorry, and O dagger over here. And if we consider the inverse, actually, yeah, sorry, I did mean an inverse over here, times e to the minus I phi 0 z. This is just the inverse of the QSP sequence. And so if we want to be able to build this, one way of doing it is to set this equal to identity. And so if we want to be able to set this to identity, we can pick phi 0 equals phi, and pi j equals 1 to d of e to the negative I phi j z O dagger of x equals identity. And we can do this actually just by picking each of them to be 1. So the way we can do it is by writing this to be pi j equals 1 to d divided by 2 of e to the negative I phi 2j minus 1 z O dagger e to the negative I phi 2j z O dagger. Okay, so if we've got this, now what we can do is we can end up picking the values so that um, phi j 2j minus 1 equals phi j equals negative 1 to the j. Under these circumstances, what we'll end up doing is we'll end up getting a situation where um, we end up doing the following. We will end up getting this to be pi j equals 1 to d over 2. These, oh, sorry, negative 1 to the j times pi over 2. Okay, then what will happen is these guys are going to end up forming a negative I j's over here. So we're going to get negative I z from this, and we'll have O dagger, and because of this minus 1 sign, we'll get I z over here times O dagger. But recall that we ended up assuming that O of x is equal to ry of 2 arc cosine of x. And thus, z O of x, z dagger equals ry inverse of 2 arc cosine of x, which is just equal to O of x. Therefore, this is just identity e to the minus I phi z. And thus, we can always end up achieving that case as well. So what this ends up implying is that all case of degree p equals 0 can be achieved by a choice of phi. Okay, wonderful. So that ends up showing our base case. Now what we need to do is we need to be able to talk about how to build higher order polynomials. So assume that all valid polynomials of degree less than or equal to L minus 1 can be synthesized using this method. Okay. Then, if that's the case, we can end up trying to build our target, P of x. We could always write it in terms of just adding an extra term, xl, to a polynomial that we have, pl minus 1 of x over here. And then q of x, we can always end up writing as beta l minus 1 x to the l minus 1, because it needs to be a valid polynomial, plus q l minus 1 of x. Now, because of the assumptions that we ended up making, we have that that we have to have that p squared plus 1 minus x squared q squared equals 1 for all x. Because we made an assumption that it must be a polynomial with respect to our three criteria. Thus, the only way we can end up having this is we have to have that alpha L squared x 2L minus x squared BL squared x to the 2L minus 2 has to equal 0. Why is that? Because when we take a look at this expansion that we end up getting in this, we can look at the coefficient of the highest order term in a polynomial. The highest order term in a polynomial is going to be simply the AL squared x to the 2L from this guy over here. And then we need to worry about the same thing from the Q. We will have from that beta L squared from this, and the product between the two, which is just x to the 2L equals 0. So what this ends up implying is that since this has to be true for all x, the only way that this can be true is that the alpha L's have to be equal in absolute values to the beta L's. Okay, so now, next up, what we're going to do is we're going to say that if we end up trying to look what happens when we're going through and peeling this off, then we end up getting that p q star square root 1 minus x squared minus q square root 1 minus x squared p star e to the minus I phi z o dagger. Now, just to take a look at what this is over here, this is the QSP sequence that we've got. This is the kind of like the previous stuff, and we're just trying to unpeel this one layer at a time. So what I want to be able to do is I want to be able to show that using these properties that we have for the coefficients over here, by putting in the next term or the next inverse that we have, and that's not phi, this is O over here, we can actually peel the degree that we end up getting a P down by 1 in order to be able to build the right sequence. Now going through what we, and just doing the 2 by 2 matrix multiplications, we end up getting e to the minus I phi x p plus 1 minus x squared q e to the I phi minus 1 minus x squared negative e to the minus I phi p plus x q e to the I phi. Now we're going to have its complex conjugate down below here, 1 minus x squared times negative e to the now I phi p star plus x q star e to the negative I phi. And now we're going to have the complex conjugate of the upper left element here, which will be x p star plus 1 minus x squared q star e to the negative I phi. Okay, great. And so now what we want to do is we want to pick the phi to lower the degree and show that it is a valid polynomial of degree 1 lower. And this, by our induction hypothesis, will do the trick. So we can end up seeing that the coefficient that we end up getting from the expansion of p will be removed if we end up taking the leading order term that we have in the p's and the q's and getting them to cancel, which will be e to the minus I phi alpha L minus e to the I phi of beta L minus 1. That's just by taking the beta L minus 1 x to the L minus 2 term from here and taking the alpha L x to the L minus 1 term from this guy, or sorry, x to the L term from there. Sorry, should be L minus 1 here. Okay, so taking that that over here, we would like to choose phi so that this term that's kind of ugly in that expansion vanishes. So we can just isolate this, and we end up getting that um, that e to the negative 2I phi is equal to beta L minus 1 over alpha L. So then we just end up picking this to be true. Now, why do we know that this is true? Well, we know that from our previous discussion, beta L minus 1 is equal to the absolute value of AL. Therefore, this is unit length. And because it's unit length, this implies that phi is real valued. That satisfies this, which again is happy because that means that that we can always end up picking a phi that will lower the degree down by 1. Doing the exact same thing, so that this means p lowered by 1 degree. Now, going through the exact same thing, we end up seeing by expanding this the q term that we have up here, we end up getting that e to the negative I phi alpha L plus e to the I phi beta L minus 1 equals 0 if we want to lower q by 1 degree. And then we can go through and we can see that the same choice implies q is lowered also by 1 degree. So by picking our phi in that appropriate way, we can always lower the degree by 1 by assumption. If p is even, q is odd, and thus the lowered degree is of definite parity, and p comma q are opposite. And further, we have that if a degree of p is valid, it's less than or equal to d, then this implies that the degree of the reduced one, I'll call it p tilde in this case, is less than or equal to d minus 1. And this implies also that it's valid. because of the fact that it's in a unitary, we also know that it satisfies the sum of, we have that p tilde squared plus square root 1 minus x squared q tilde squared has to be equal to 1 because it's still embedded in a unitary after doing this lowering that we have with this part. So this implies that claim 3 holds. Thus, we have lowered a valid degree L key to a valid degree L minus 1 polynomial by choosing this. All degree L minus 1 polynomials can be built by a choice of phi by assumption, and therefore by induction. All polynomials can be constructed by a good choice of phi. Okay, and this implies that our proof is complete. So we've now shown that we can always end up picking for every valid polynomial the set of phi's, and the way that our proof ended up working was that we proved a base case where we can always do it. It was a trivial d equals 0 case. And then what we did is we just went through and showed that we can always take a higher degree polynomial and reduce it to a lower degree polynomial. And that's valid. And then by induction, that gave us an argument that showed that we can actually find angles phi that will implement any valid polynomial. And similarly, since we showed that all valid polynomials can be built using a QSP circuit, that shows our if and only if statement. And that's how QSP works. And through it, we can build any polynomial we feel like. Now, next time, I'm going to take a look at this and show how we can use this in order to do optimal Hamiltonian simulation. Thanks a lot. See you all next time.